Well, before I start with my presentation, I would like to remind a few figures, and I know people hate figures, but they are important to understand problems. Just to put the scene, I will quote two categories of figures. First, the size of the various industries in the energy field. And to measure this size, one very simple way is to give order of magnitude of their annual turnover. How much are the sales in the oil industry, the gas industry, the coal industry, and so on. So I just quote very rough order of magnitude, but they are important to keep in mind. By far the largest is the oil industry, which has roughly $3,000 billion yearly turnover. You take the daily production, you multiply by $100 per barrel, and you will see that's $3,000 billion per year turnover. The second one is the gas industry with a bit over 1,000. So in fact, oil and gas is the same, so it's 4,000 for these mammoth companies. Most of them being national companies, by the way, not private. Third comes the coal industry, very close to the gas as a turnover worldwide, roughly of the magnitude of $1,000 billion. Then we drop brutally by a factor of 10 times. The next largest industry in energy is nuclear, with roughly $100 billion world turnover, sales of electricity from nuclear energy. Then we drop a little more to come to hydroelectricity. That's roughly $80 billion turnover worldwide. Now we come to the other renewable. That's roughly $50 billion turnover today. But don't forget that it's subsidized on average worldwide by 50%. Well, let's say that there's a 100% subsidy. This electricity produced either from wind or from solar is sold to the grid at, on average, twice the production costs of the electricity by traditional means. So the real, if it was really on the market, the turnover would be $20 to $30 billion. So we are speaking of completely different size of industry, and there is a time to change from one system to another system, and we tend to underestimate that time. I'll come back on that. And especially we tend to underestimate how fast the renewable can grow. Obviously, they have an important growth potential, but at what speed? And what are the limitations? That will be, I'll try to give order of magnitude. There was the second set of figures I wanted to give, which are the carbon emission for electricity generation. You can find these figures in many, many brochures, but they never give you simple order of magnitude. They always complexify the system by giving much too many detail. Let's stick to the order of magnitude. If you take a coal power plant, it will roughly produce between 1,000 to 800 grams of CO2 per kilowatt hour. 800 grams are really the state-of-the-art power plants. If you go now to gas power plants, here you have two categories completely different. The open cycle for the short peak period, and that's also roughly 800 grams per kilowatt hour, the same as state-of-the-art coal power plants. Then you come to the much more efficient, twice more efficient combined cycle gas plant, which cannot run on peak, by the way, so it's very important. These are roughly emitting 400 grams per kilowatt hour. Let's come to renewable. A professor from Germany, which I have not identified, mentioned 200 grams as an order of magnitude for solar. I do agree with that. And then you come to something like 50 grams, depending how you make your calculation, both for wind energy or for nuclear. In fact, it's probably even less than 50. If you see last year, the emission in 2011 of EDF, Électricité de France, which is the largest electricity company in the world, their emission last year was 31 grams per kilowatt hour. So you see, you can achieve very, very low emission in various ways, either by a very high percentage of renewable or by a very high percentage of nuclear. That's the French approach. Now let's see the limitation to renewable. We will take them very quickly, and that will be the end of the introduction. First, biomass. If you take the world energy supply system of commercial energy, not taking the wood picked up in the villages, which is outside the commercial system, today, biomass, commercial biomass, is no more than 2%, 3% of the energy supply system. So what could be the asymptote, the maximum? How much could we push that? We had some good indication with the presentation of the pellets. Remember, to produce 400 million tons, that's the potential of a country like Brazil, you need a very substantial surface, you remember, 25 million hectares, and that's the equivalent of 200 million tons of oil. So if you wanted to push, let's say, very, very high the biomass, and let's assume you do it the most efficient way, which is the pellets, it's just to simplify the figure, you could probably push to 2 billion, 1.5 billion, 2 billion tons for the planet. That is equivalent of 1 billion tons of oil equivalent. That's roughly 10% of the world primary energy supply. That's the asymptote 50 years down the road. There is no way you can do more than that. You would have even to achieve that to sacrifice a lot of present arable land which is used for crop, for food, and you would create a lot of disturbance to produce that. So even creating a lot of disturbance, your asymptote is 10%. So don't dream of 50 or 100%. It just doesn't make sense. Look the figures. Let's come to wind. Wind, it has only one possibility of being used today, is electricity generation. The limitation here are a combination of economics which are not simple to summarize. First, you have the generating cost itself. If you take on average today in Europe, the onshore wind system, it's roughly 100 euro per megawatt hour. That's an average cost within Europe. Offshore, it will be more like 150. Even if the efficiency is greater, the costs are much higher. And as it was mentioned, that's already represent in Europe 100 gigawatt installed, generating 6% of Europe needs. So let's think about these figures. 6% for 100 gigawatt, it means that on average, this system deliver electricity 2,000 hours per year, roughly, on average at peak capacity. They work as if they were producing 20% of the time. Obviously, this is an average. So you need a backup for the rest of the time. And that is the biggest limitation on the first large limitation on the possible development of wind is that above a certain percentage, you will need a backup, which you will add to this cost, which I mentioned, of 100 or 150 euro per megawatt hour. And that can be quite important. It can increase by 50% or more the cost, because the backup has to be there permanently. The second additional cost, hidden cost, is transmission cost. As soon as you start reaching, let's say, the 10% type of figure, you need transfer line all across Europe, and that was said also by the lady from Berlin. And today, it's nearly impossible, let's say, to build in the next 20 years the capacity which would allow to transport freely. Let's say if we had 10% of our electricity in Europe from wind, it would be extremely difficult to have the connection necessary for that. So I would put as a kind of maximum for wind power 15% of the electricity supply. So even if you assume that electricity will gain in percentage, and that by 2050 it will be 50% of our energy, primary energy, so 15% multiplied by 50%, it's 7.5%. So let's assume, round it to 10%. So the potential of wind is 10% of our energy. So we add biomass plus wind, we are far, far from our goal. So how are we going to do? And that's what I would try to show now. This is a study. I will just comment the right part, which I published in 1999, which was published in German in Erdöl und Kohle in year 2000. So you can see the figures have not changed. They are the same than 12 years ago. When I published that, people say, well, why do you see a peak in oil? I put the peak oil in 2020 at 100 million barrels per day. Today, these seem optimistic figure, not pessimistic. At that time, everybody say you are crazy. IEA tell us that we can go to 130, 150 million barrels per day, so you don't know what you are talking. Well, I was head of strategy for Total, so I think I knew better than IEA. I had better access to the data. So today, I've not really changed much my vision. Maybe it's not going to be 100, it's going to be 95. Maybe it's not 220, it's 215. But these are tiny details. So the basic study, I stick to it today. Look where we come from. We come from, let's say, a 10 billion commercial energy ton of oil equivalent. It's all in ton of oil equivalent. And you see that in year 2000, oil was 39%, today it's 36. Gas was 33, today it's 24. Coal was 25, today it's 27. So that has not changed, and the total is still above 80%. We are still roughly at 85% of carbon-emitting energy, and only 15% non-carbon emitting today. And out of this 15%, roughly half is hydro, half is nuclear. The rest is, for the time being, statistically negligible. It's 1%. So that's an important message. If you look at the IEA publication, be careful. They completely overestimate the figure for nuclear vis-à-vis hydro because of convention, which to me are nonsense. I think those figures are far more representative because the hydro kilowatt hour has the same weight whether it's hydro or nuclear in this table. Let's come to 2050. We will have increased our population from 6 to 9. Today we have crossed the 7. You see that we could reduce the carbon emitting to something like 66% here. Maybe if we are very efficient, we can come to 60%. I don't know. But still, the majority will be there. And the problem there is what is the spread from the non-carbon emitting. Here is a spread in which Fukushima was not included, which will obviously put some delay and additional cost on a relaunch on a worldwide basis of nuclear, but I don't think it will change very much the phenomenon. because we have no choice. We don't have enough time to develop the renewable at the scale we want. And even there, you see, I've multiplied by 20, a factor of 20 times the renewable on this period. We are more or less on that track, but I don't think we can do much better. Some country like Austria can do much better, or Ireland or Switzerland. But if you take the bulk, and if you see that most of the development now is in China, India, and other similar countries, on a world basis, I think 10% of renewable or 11% in 2050 is probably already an important objective, especially when looking at the limitation I mentioned already for biomass and wind. I left solar out. Let's forget 2100 because it's too far. Just one slide to show you why is oil extremely difficult to replace in the transport system, whether it's air transport or ground transport. It all boils down to energy density, either volumic density or massic density. Here you have the kilowatt hour per kilo, kilowatt hour per liter, and you see that liquid hydrocarbon are so far better than any other solution, hydrogen, gas, whatever you want, or the electricity even. So it's a way how we could solve the transport problem. I have limited time, I won't show that, to go to the... Obviously, we have another solution if we don't want to have electricity penetrating in the system, but this is also something we don't wish. We could very quickly compare wind and nuclear. Basically, no CO2 emission. The question of surface, which is quite different, 10 megawatt per square kilometer for wind, 1,000 to 1,500 megawatt. One is not available on coal. It comes when there is wind. One is base load or on coal. You can, in fact, rather easily modulate. The unit investment on one is small, the wind. The other one is very large. But the investment per megawatt installed is not very different. And per megawatt hour, it's far smaller for even a new plant with very high costs like an EPR, the former French-German reactor. One would last 20 years, the other 60 years, in fact. One has no fuel cost, the other one has a fuel cost, but very marginal. 5%, the uranium is 5% of the cost of the kilowatt hour. So that gives you 10 to 20% max in electricity mix. I told you 15%, that's the middle of this range. Now, let's come to the last one, which I left for the end, because it's the most fascinating, solar. Solar is the area where you have had the most progress the last 20 years in terms of percentage of increase in the system, in terms of cost decrease per unit. So solar is really fascinating. You see, it's growing at something like over 16% per year. So it's the fastest growing worldwide. And there are three markets, in fact. You have the solar farms, concentrated system. You have 1/3 the commercial rooftops, and 1/3 the residential. And completely off-grid is a very small market. It's 2% of the market. Initially, remember, it was 100% of the market when it started. 30 years ago, I remember when we created our first solar company, and I was one of the creators, it was all off-grid. We had nothing else than off-grid. So today, it's completely reversed. 98% is grid plugged. Second, we are closing much quicker than we believed the grid parity for the roof system, not for the concentrated system. And that's quite interesting, and the drop was extremely sharp the last 2 years. Here is 2008, 2010, 2012, and you see all the components of the system, from the silicon itself, the wafers, the cells, the modules. You have all the components. That's a breakdown. And you see that you had a cost reduction already of something like 50% in 2 or 3 years. And you still expect on the coming years a much quieter, but 6% per year decrease in unit cost, which no other industry can boast of being capable of doing. And if you look now at the grid parity in euro per kilowatt hour, you see Germany and southern Italy. You see that southern Italy, it's already economical for certain residential areas to build without subsidy. You have subsidy, but even without subsidy, it could start being economic to have rooftop on residential. And in Germany, the same would happen a bit later, because you have less sun, obviously, around 2015. So my message for solar is very different from the other renewable. We don't know where is the limit. If we can continue to progress the way we have progressed, I would say, maybe it looks like a joke, the sky is the limit. You know, the big advantage of solar, that today you don't see limitation on the progress. We know what would be the best wind turbine 30 years down the road. It's mechanics. We know how much we can extrapolate. All that we can predict. If you are in a good engineering firm, you know that. You cannot predict what we will be able to achieve with solar. So we have one wild card, which could maybe allow us not to develop massively nuclear, and that is solar. Here is the last graph. You see a comparison of the electricity cost, solar with different assumption, and the other way of generating electricity in Europe. And you have all the figures, either in dollar per kilowatt hour or in euro per megawatt hour, in both cases. And these are 2011 dollars and 2011 euro. So I've finished. Oh, no, sorry, that's conclusion now, conclusion. There are 3 slides of conclusion. The first one is for energy planners and governments. By mid-21st century, the share of fossil fuel in world commercial energy is expected to decrease, but from 84% today to 66%, and still more than 40% at the end of the century. So that's a very, very, very worrying message in terms of climate change. The decrease will have 2 causes. The peak oil, I don't change my figure for the time being, 100 million barrels per day plus or minus 5, around 220, plus or minus 5 years, and peak gas at 5,000 cubic meter per year, plus or minus 500, around 230 to 40, combined with the CO2 emission restriction. Second, still for energy planner and government, non-carbon emitting source will have to fill the gap. Most renewable energy can cover only a very limited share of this gap. Hydro, biomass, wind energy, geothermal. Each of them face strong economic or physical economic limitation. The bulk of the remaining gap will have to be filled by a combination of solar and nuclear. We will need to wait probably around 2020 to know whether solar can be developed at such a scale that we don't need to develop nuclear on a very large scale. Last conclusion for students, for academics. Well, it's a paradox, but during the 21st century, it will still be an oil and gas industry golden age, despite the decline, because the price will be high, and it will be more and more high-tech. We will produce more and more sophisticated, let's say, non-conventional hydrocarbon. Therefore, there will be a huge need for top scientists, technicians, and so on in this industry. It will be obviously a golden age for all renewable energies. Energy will be expensive, and there will be a premium for non-carbon emitting sources. And obviously, it will be the golden age also for nuclear, despite what we had in Fukushima. For all students, then, I think it's clear they can engage into promising career in any of the energy-related fields or industry, whether they like oil or they like renewable or they like nuclear or CCS or whatever. Thank you.
Thank you, Professor Bauquis. Please stay up here with the microphones to take some questions. Yes, there is a couple of questions. I think you had some quite provocative statements, so let's hear. Please, where's the microphone? Who's got the microphone? I got the microphone.
Yeah, I really would like to update some of the figures, especially about the emissions, the CO2, the grams of CO2 equivalent emissions per kilowatt hour for solar.
Yeah.
Mariska de Wilde from ECN and others, and I and myself also, have done many life cycle assessment calculations on solar, all kinds of different technologies. And I'm not sure what 12 years ago, what the emissions were, but I can tell you today that for polycrystalline and monocrystalline solar cells, it's roughly 20 grams, not 200, 20 grams of CO2 per kilowatt hour. And when you calculate, I just want to make this point, when you calculate the carbon footprint, you take, it's a calculation over the lifetime of the energy device operating. So if you make a solar cell, you put energy into it, but then you operate it for 30 years with no emissions. And so it cannot be, and it is not, that a solar cell only emits a fifth of what you get from coal. Even if you were to make a solar cell from 100% Chinese coal electricity, you would indeed double, and I have done this calculation, you would double the emissions to 40 grams per kilowatt hour. But because you then operate this solar cell for 30 years with no emissions, it's still better than almost every other kind of renewable energy.
Well, on the calculation difference, first you took 30 years, I took 15 years. I think people change the panels every 15 years. Okay. We'll discuss. It is very low. I think we generally.
Agnès Sinaï from French Press. I was wondering what was your vision of the future of Japan, the energetical future of Japan? What will be the mix, and is it a laboratory of the future?
It's really a political process in the good sense of the term. They have stopped today all their nuclear plants, and they can still survive. Obviously, they are Japanese. We would be very, very reluctant to accept the kind of restriction they are accepting, which means they have lost, let's say, nearly a third of their generating capacity. They have increased, obviously, immediately their imports of coal. They had some mothballed plant of LNG. They run all their gas plants at full power, and this had a lot of effect on the ripple effect on the price, on the availability of LNG, and so on. But still, they run with 20% less electricity than they used to do, and they do it, which is extraordinarily remarkable. We have to learn a lot about that. Now, for the future, the big debate, and it will take probably 2 or 3 years, is at what speed they will reopen and how many of their nuclear plants will they reopen. And the trauma in the population is such, because this decision needs the agreement of the local population, the local prefect, and so on. Nobody, except if you were in the Japanese politics, but even if you were in the Japanese politics, you cannot predict that. My own prediction is that it will reopen in the next 3 years, 80% of their nuclear plants. But I could be wrong. If the population is against it, and the Japanese, when they are against something, they can be extremely stubborn. You know, the Narita airport was terminated, and it took 6 or 7 years to open it officially because people didn't want it. So I cannot, my forecast is purely based on a kind of past behavior of the Japanese, but there could be a different behavior this time.
Okay, thank you. Let's get some more comments. The microphone is back there.
Just on the life cycle emission of solar cells. What I quoted were numbers between 90 and 190 grams per kilowatt hour electricity generated. And the 90 grams are from the Öko-Institut Darmstadt, very much in favor for solar energy from the year 2006. So this is a quotation from 2006, and recently we had a debate with Hans-Joachim Fell, which is the champion of solar energy in Germany, and I quoted these numbers, and he said, yes, they are right, but if we take very advanced systems produced in Germany and not in China, then the figures are better.
Okay, so that's a detail. I'd like to give the floor to Robert Hirsch.
Excellent presentation. I think very realistic, the kind of thing that I'm used to seeing in oil companies, and I've seen a couple of them. So it may bother a number of people in the audience that you haven't bought into some of the hopes of some folks, but I think you're being realistic. A couple of questions. One question is you talk about peak oil, and you showed significant oil production out in 2100, and I'd like to understand that. Number two is a question of what do you use, what do you favor, what do you think would be the appropriate backup for intermittent renewables, namely wind, and you didn't mention the backup necessary for photovoltaics. That's the second question. And the third question, why is it that Total has had the guts, the willingness to speak out about the reality of peak oil coming at some point, whereas the rest of the oil industry has chosen to not speak out on that subject?
The first one, you are surprised that I show still some production, and not negligible production, by the end of the century. 1 billion ton of oil per year, roughly. It's not a small thing. Huh? It's a quarter of the peak, but still, it's still substantial. I believe we will have no choice but to produce a mix so that we can have a transport system which works. So I made a lot of assumptions on the transport system, and we will need 4 billion tons of oil equivalent for the transport system. 25%, in my opinion, will come from oil. That's on the demand side. On the producing side, I work with much higher figure for ultimate reserve than most people. I work with 6,000 billion barrel ultimate because I think we have seen only the beginning of the non-conventional. We will have more and more of that. And I think the limitation will not be in the resource. The limitation will be on the cost and on the CO2 emission. How much restriction, how much will be the cost of emitting CO2 in 20 years, 50 years, nobody knows. But I don't believe we will be constrained by the resource at that time. Obviously, it's a declining curve, so one day we are completely constrained. It's already a big constraint to lose 3/4 of your capacity for an industry.
Okay.
That's all I can say.
What about the guts?
The third one, it was Total, no? The second was backup for renewable. Well, here it would be, let's say, quite technical. How much do you need for how much percentage on your grid? Huh? Clearly, it's not the same problem for solar, which is much more predictable. than for wind. Solar, you have it every day with different nebulosity. But wind, you can be in Europe for 10 days, even extreme case 15 days, without wind on the whole of Europe. So you cannot transfer from the south to the north, you have no wind. And you have to be ready for that and to have the necessary backup. And you don't know when it will happen. And generally it will happen during peak consumption period. Today you have a winter peak and a summer peak starts to come with the air cooling and air conditioning. And these are the two seasons, the extreme summer and the extreme winter, where the anticyclonic standstill can come over Europe. So you have to cope for that. And that's how you calculate your backup requirement.
Okay, I think
the last one, what was the last one?
Why Total had the guts to say there is going to be a peak of oil?
Well, when I produced my study, I was still with Total, I was head of strategy for Total. I insisted to publish it, and they finally say, well, let's study it in detail. You have studied that in your own little corner, and they find it was an interesting subject, and finally they stick their neck out, but only 6 years back, and since then they make statement on that. They are the only company who made statement on the peak.
Thank you very much.